This episode is brought to you by WeatherGuard Lightning Tech. At WeatherGuard, we make wind turbine lightning protection easy. If you're a wind farm operator, stop settling for damaged turbine blades and constant downtime. Get your uptime back with our StrikeTape lightning protection system. Learn more in today's show notes or visit weatherguardwind.com/striketape.
Welcome back. I'm Alan Hall.
I'm Dan Blewett, and this is the Uptime Podcast, where we talk about wind energy, engineering, lightning protection, and ways to keep your wind turbines running. All right, welcome back to the Uptime Podcast. I'm your co-host, Dan Blewett. On today's show, we've got two great guests. Amolik Badesha from Orbital Composites is here, along with Cole Nielsen. So Amolik is the CEO and Cole is the founder and CTO. So a really fascinating conversation. Orbital Composites is doing some really interesting things in the wind industry and others. Alan, what were some of your takeaways from the conversation today?
Well, Orbital Composites is bringing a new concept in composite technology in the 3D printing area, where they can print continuous fiber. Now that's a significant difference than the tape placement and or the hand layup that we're currently doing on a lot of wind turbine blades. So they can fiber place bundles and impregnate them with a resin or a thermoplastic as those fibers are being laid down into a composite part, which is a revolutionary new approach to making wind turbines, which just opens up all kinds of possibilities in terms of cost savings, aerodynamics, structural design. It's just a really new useful tool in our toolbox of how to make composite wind parts.
Yeah, I mean, their vision's really big, obviously, one of which is to have sort of micro factories that they can drop at a wind turbine site, print the blades on site, eliminate a lot of the logistical problems, the transport problems, and you know, it's definitely somewhere that all these industries are going, like on-site mobile construction. As we talked with the founder of Cobod, which does concrete 3D printing. They're doing a very, very similar thing, but obviously with composites, this is also a really complex industry. I mean, I don't know nearly as much about composites as you do. You know, you've been in the aerospace industry, your whole life. Why is composite technology need to change, and why is 3D printing potentially so disruptive to that industry?
Well, the benefit of composites, you can apply strength where you need it and eliminate weight and cost where you don't. And if the issue has been is that in order to use composites, you kind of got all this extra pieces to it, which are the way we have to apply it and use it now is sort of inefficient. So we love the composites technology. We don't like other things that come with it, like autoclaves, the freezers for thermosets, just all the infrastructure pieces around it. 3D printing eliminates most of those and brings the efficiency of composites to its maximum. So you can print fiber where you want fiber and don't print it where you don't need it. And that would have all the extra infrastructure pieces that go along with it. So it really drives down the overall cost of manufacturing and can decrease the weight and complexity of parts, which is where we want to go. So the ultimate useful pieces of composites can be brought to its maximum. That's what 3D printing does.
Yeah, so again, Amolik is the CEO. He's got a really interesting background. He's an investor. He's also an advisor for RoboWind. And Cole is just, as you'll hear in the show, just such a diverse background in aerospace, in composites, in 3D printing. Like, he's got his hands in everything. Both of them just really brilliant minds. So it was a really exciting conversation today. Just from them, and just, again, getting a glimpse into the future of what wind energy could be. So without further ado, we're going to take you to our conversation today with the guys from Orbital Composites, Amolik Badesha and Cole Nielsen. And we are here joined by Amolik Badesha and Cole Nielsen from Orbital Composites. How are you guys doing?
Oh, pretty good.
Thanks for having us.
Yeah, appreciate you guys coming on the show. So, to give our listeners in podcast land, if they're not listening on video or watching on video, a chance to kind of differentiate you guys and get started on the right foot. Amalek, let's start with you. So, as CEO of Orbital Composites, what are you focused on right now? And can you give us a little bit about your background?
Sure. Yeah, my name is Amolak Patesha, CEO at Orbital Composites. And I actually came into Orbital, Cole and I, our kids go to the same school, and that's how we met. One crazy guy talking to another crazy guy, and boom, you have a you have a team.
Here you are.
My background was actually in the semiconductor industry, and I've done many different roles at Broadcom, which is a well-known semiconductor company. And I joined Orbital because Cole, who's the crazy scientist and the founder and really the visionary of the company, and it's just the vision of the company has been just struck me from day one, is that okay, there's something special going on here, and I want to be part of it, right? And then spent a lot of time learning about what are our long-term goals. So as in my role, my primarily focus is really taking this fundamental robotic 3D printing technology and find some super compelling applications where we can apply this and really have a very large impact. And we're fortunate that we can have that kind of impact in multiple industries. But we focused on wind kind of by accident. Initially, we had a customer that reached out, one of the bigger ones, who wanted to get into the whole 3D printing thing. And that prompted us to really dig very deep into the industry itself. And that was the journey where we started on back in 2017. And now we're at a point where, we're really getting ready to start some really incredible scale-up demonstrations coming up where we can show how we can print these very large turbine blades and completely change the economics of how it's done. So our goal is, 25% cost reduction, recyclable blades, on-site manufacturing.
Yeah, those are, three huge ones, because we talked about a bunch with a lot of different guests on our show and just in general that it's just really expensive to get these wind farms up and running. So Cole, let's hop to you. So as the CTO and co-founder or founder of the company, tell us about your background, because like Amalek said, you've come a long way as far as where the company was at the beginning and developing technology, and I know you've iterated a lot over the journey to this point. So tell us about you and what's led you here.
Sure. So Cole Nielsen. I'm educated as a spacecraft physicist. So if you want to think about mission design, and that means orbits, that means the magnetic field of Jupiter, that how do you build sensor payloads for that, but how do you plan the mission as well? So that's some of it. And the other half is computational math, building calculators and lots of visualization to go with it. And kind of, I've also always worked in IT. So you put all these things together, and we can use computers and new kinds of math to solve different problems. So initially, then, when I wanted to start a company, I looked at wanting to build very fast helicopters, and really kind of the conclusion I came to after studying how these things could be built and where the limitations are. What we ended up finding out was that you have automated fiber placement. That's these super big robots, potentially 120 feet long, and they're going to lay down these very high quality, perfect, tapes of carbon fiber. And those machines, they don't get very small, however, right? And then you look at 3D printing. 3D printing can make small things very well, lots of curves, lots of open cell foam architectures, low density meshes, things that the fiber placement stuff just can't do. Except the fiber placement stuff is incredibly strong and 3D printing is anything but the shape is right. So it seemed to us that right in the middle of size and overlapping the benefits of both, there should be a new technology available. So that's kind of why we decided to build a nozzle inside of a nozzle, put carbon fiber in the middle, and just the same way that you insulate wire, we could go ahead and use the insulation to glue the threads together. So now you have carbon fiber and 3D printing completely merged. And the size of the robot you pick puts you at which length scale you're going to choose. So then in this part, we developed these tools. We started installing them on different robots around the world in these different research labs for different industries. And one of the things we found was that robots are really challenging to deal with, like incredibly challenging. And what's going on there is that you have a bottom-up embedded computer or embedded device method, right? Where you say, okay, I've got this PLC, and the PLC is going to control the switches and the knobs, and we're going to run everything at 24 volts. And every single time you want to build something new, you have to cut this piece of wire and stick it into the computer and do all this stuff. Well, when you really look at what a car factory is today, it's a collection of robots that are scattered in a production line. They're basically treated like small teams of people that build an assembly and then they go to the next station. That's very different than being able to have all 1,000 or 2,000 robots in a single factory operating as one machine. There's a big difference there. But coming from the IT background, and you look at the evolution of the internet. So let's say a hard drive dies at youtube.com. Your video doesn't disappear from the internet. Why not? What's going on? What is the cloud? And so what we've done is we've fundamentally taken industrial manufacturing robots, given them new calculators to do motion planning and so on. But those individual devices are now cloud devices, cloud robots, which means that we can start to add more, an unlimited number of robots to a single system. And from there, we can have hundreds of robots potentially printing onto the same wind turbine blade at one time. So, in the process of going through all this, after we invented the first tool, I was really struck with the notion, hey, you're starting to produce between carbon fiber, copper wire, and some kind of plastic. You're looking at producing the majority of an aerospace system, of either a satellite or a drone. Now, if that's the case, maybe if you have 5, 10 tools in a single box, you could do the whole thing. Well, if you could do the whole thing in a single box, you could move the box.
So you got to the point which is where I want to go now, which is, what is Orbital Composites' vision? So it's everything contained in essentially a containerized portable factory. Is that right? Where now we can plop this down in the mountainside where we're going to have a wind farm site, and we can print a blade from start to finish right there, eliminating a lot of logistical problems and all that. A, is that right? And B, can you take me, and obviously like our listener base, varies. We have some super tech savvy folks, and we have some people, like I would say I'm the most layman person in this conversation right now. So take me through the flyby, the overview of what it is you guys are trying to do, and taking that high level IT and engineering background and making it into a viable product for the wind industry.
Sure. I think there's kind of two answers to this. There's the guiding light, the North Star, if you will, of where we're trying to push the technology. Ultimately, that's Mars. If you really think about it, you're not going to go over there with a truckload of styrofoam cups and then throw them out the airlock when you're done. No, you're going to recycle.
Americans would do that, Cole. Come on, that's exactly what we would do. We're going to pollute as many planets as we can until we're just done.
Maybe so. But to me, it just seems, cost-wise, much more efficient to use a circular economic model in that context. And if you really look at what it takes to generate energy, get transported, grow your food, recycle your waste, you're really sort of encapsulating the human condition if you want to survive on another planet with limited resources without persistent refilling.
Yeah, I figure that's kind of where you're doubling back to. So your styrofoam cups example is let's create our own styrofoam cups, and when they become trash, let's recycle them and use them again
as
for something
plates
new.
or forks or more cups.
With that being said, 3D printers aren't printing fiberglass. So, Moloch, I'll throw this to you. You guys are interested in printing blades out of thermoplastic. Why hasn't that been done yet, and why do you guys feel like that's the way going forward?
Well, before I answer that, let me address your last question also, because you asked why on-site mobile manufacturing, right? So the key thing is there is a transportation problem, right? We can't transport these blades to these sites, the Goodwin sites. Because they keep getting larger and larger, a lot of sites get inaccessible. And we've all seen pictures of these gigantic blades stuck on the mountain somewhere. So that's a real problem. And on-site manufacturing, there's been studies done by Department of Energy and even internationally in Europe, specifically highlighting as mobile manufacturing as one of those potentially very large disruptive ideas that unlocks all of a sudden you can start to continue to grow the size of the blades and create more energy from a single turbine, which ultimately means the cost of wind continues to go down. And I would add that there's also this new concept that's coming around, which is the concept of modular blades, right? So that's actually another way to try to solve the same problem. But even there, ultimately, these blades are going to continue to get bigger and bigger and bigger. You're still going to hit that same problem eventually. So
Right.
Mobile manufacturing has tremendous benefits. So that's just one thing I want to make sure everybody understands that.
Yeah. And to touch on the modular blade thing, I mean, Alan, you and I have talked about this. Those haven't, I mean, I think they're still relatively new, right?
They are.
And those
Relatively, yes.
joints where the two-piece blades come together, I don't know if there's data yet on how those fare 10 years out. That the blade being 108 meters long now, that seems like something you want to avoid if at all possible, which would make the mobile manufacturing just another benefit where, obviously
Right.
the least complexity we can have in any engineered object, the better.
But we're also talking about sort of incremental costs and cost savings in the overall lifespan of a wind turbine. So part of the capital cost you have when you manufacture wind turbine blades like you do right now is that you manufacture one, you put it in the parking lot, it sits there for 6 months, and then you ship it for 3 months, and then it gets installed. So that whole time from the time you purchase a material to the time it's actually producing energy is lost capital. Right. And that's an incremental cost you don't think about. But if you can eliminate those incremental costs of having products sitting out there doing nothing, not making you money, and you can eliminate those, you can recapture some of that value back. And that's what the mobile on-site manufacturing is going to do. It's going to reduce the overall cost of the creating and operating a wind turbine. And that's why it's so important, because we need to get rid of those big structural costs that we have built into the system right now.
That is a fantastic point. That's a really good point. And then back to why thermoplastics, right? So in terms of the technology, there's a couple of challenges, right? One is you kind of have to prove it out, right? So the good news there is that the National Renewable Energy Lab in the US in Colorado, they've done some test blades at small scale, and they're proving out the materials. Similarly, there's a large project planned in Europe to take that same material set and then show a much larger blade being produced with thermoplastics. So the technology is maturing, and now there's motivation. So we believe this will happen, at least from the technical side. Then if you look at it from the business side, you have the cost challenge, okay? Thermoplastics, a newer class of materials, the volumes are not quite there yet, right? So naturally, they will be a little bit more expensive, right? So this is where now you have to get creative and figure out how you can support that or justify that cost increase. And we think there are plenty of ways to do that. We're talking to potential partners and customers about that, how to actually, we think it will be same cost or lower. If you do things right and really think through the circular economy, this will actually be much lower cost in the long term. And this is where you have to start talking about lifetime costs of blades. And so we strongly, firmly believe in circular economy, recyclable blades. We think that they will actually give you better performance, ultimately, better repairability, and lower cost, because somebody has to pick up the cost of these things going into the landfills.
Cole, I want to kick this to you. So one thing you mentioned earlier, as you're introducing yourself, you talked about fiber placement and the matrix in a 3D printed object. So, and we've also talked about in our pre-interview open chemistry. So can you talk about those two things and help someone who maybe doesn't have the deep scientific background understand what's the difference in fiber placement offered by 3D printing, and what is the open chemistry benefit of using thermoplastic?
Oh, a fun set of questions. I like it. So we have a couple of different things going on. When we look at the motion platform with which we are printing, this is a huge constraint on what the fibers can look like at the end. So if you have an XYZ, 3 axes by which you can move only, you're going to think about the objects you're going to build a flat layer at a time, all the way up. If the nozzle can't tilt in any direction and you can only translate, you're going to start stacking layers all the way up. And those layers, they're going to want to split. This is one of the big problems with 3-axis 3D printing. You could be using lasers, it doesn't really matter. Powder systems, extrusion systems, the motion mechanics are really defining a huge amount of your material's properties because they're defining where the layers are. Now, if you're using a robot, actually one of the things that we've done is we've actually gone all the way to 12-axis 3D printing, where we actually have a single object being held with one robot, and then another robot.
Do you have to take it into the matrix to do 12 axes? How many axes do you get here just in our current?
No, yes, I live in the matrix. We built our own operating system, and all the text is green. But no, if you think about 5-axis printing just for a second, you're able to have X, Y, Z, but also tilt this way, tilt that way. Well, that's pretty good. Because now you can print on the wall. But the problem is you can't print on the ceiling because the motion mechanics are getting in the way. There's a limit to what a 5-axis gantry can do. Now, if you have a robot, 6-axis robot, which is not very different than your arm, you can print on the ceiling, you can print on the floor, you can print on the wall. So you can start to think about printing a tower and then starting to surface that tower. Well, now the layers, floor by floor, go up. But the wall can be made this way. Where's the layer now, right? So this, if you're going to have a crack propagate this way, it's going to hit a wall, literally. Perfect. Now you're starting to change the physics by changing the motion. Where we've gotten at this point is actually 12-axis 3D printing, where we have a small object held by one robot, and we have another robot with a continuous fiber placement, and we're able to completely wrap this thing much in the same way that a spider would wrap an insect. So if you think about fiber placement for 1 second, traditionally with aircraft, those massive objects are actually nearly two-dimensional, 2.1D, 2.3D. A cylinder is a flat sheet rolled up. The bottom surface of these wings is almost exactly flat. So the material that we're printing with when we're using tape, we're doing tape placement, is not having to steer in 3D. So that actually does work. But if you want to wrap a bug like a spider would, actually you can't do that. You cannot take an automated fiber placement machine and wrap a ball. It doesn't work. You're going to get wrinkles or tears in those tapes. It's not going to work. So we've had to solve a fiber physics problem, a motion planning problem, which is a big box of math, and then you need to program these things, and that's an IT issue.
So this is where you were talking about earlier how in the cloud now all these different robots can collaborate, and so like you said, one's holding an object and they're all working sort of like as a symphony together. Do I have it right?
Sure. I mean, ideally, you should be able to have a big honking robot. One of them prints the shell of a car, and then four more come over, just like when you're watching welding, right? All these spot welders come out of nowhere, and zap, 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 zap. But why can't that be, 20 different fiber placement robots wrapping the chassis of a car really quickly? Why not? No one's really solved that, but it's fundamentally IT and math. It's not physically impossible.
So if you look at the turbine, right, you have a spar cap where the carbon fiber is used, and it's essentially flat, right? It's a flat surface that is, so people did try using fiber placement and have used it. It's just very expensive, and they kind of stopped using it eventually. But you're making very primitive, simple geometries. It doesn't allow you more advanced organic shapes that could be significantly more efficient, right? So that's the key point here, that with the printing specifically and robotic printing, it gives us that freedom where we can start imagining novel architectures where you could really start thinking about optimizing in ways you could never do before. And then it ties back to your question about open chemistry. That's a very important concept because, and this also relates back to thermosets versus thermoplastics. Thermosets, once the material has been cured, you can't go back and do anything, which is why repairing composites is such a difficult thing with thermosets. One of the beautiful things about thermoplastics is you can actually go back and then open that chemistry again and repair. And so today's repair is, stick a Band-Aid, right? Your blade has a problem, you stick a Band-Aid. Or you add some, like you fix your wall, right? You add some plaster to it, but that's not really going to fix your problem, right? It's kind of patchwork, right? But with thermoplastics, you can go back and really start to do some really nice repair work because you're working with the same chemistry on both sides. The repair patch could be thermoplastic, and you can actually be very thorough and accurate on how do you repair those things.
So would this be, so like when I was in high school, I liked welding. I had a welder. I worked on my old Bronco and some other, my Jeep that I ended up flipping.
Nice.
But I liked working with metal because if I mess something up, I gouge it with a saw or grind too deep, I could just weld on and add back the material I lost and then grind it back down to shape. I felt like with metal, I was always ahead of the curve. I could always fix whatever I screwed up. Whereas with wood, you're like, dang, I just took a chunk out of that. There's no fixing this piece of mahogany. There's no fixing this piece of walnut. Is that a decent analogy for what essentially an old blade used to be compared to what a thermoplastic blade could be?
I think that's perfect. And when you use that analogy, you can extend a little bit further into what do robots do, and how does advanced fiber placement as well as advanced sensors really help when you have the ability to reinvigorate your chemistry. So as an example, look at the offshore wind blade issue. So we have these blades are designed for 20-year lifespan, something like that. The tips of these things are 3, 4, almost 500 miles an hour for 20 years. That's crazy. I mean, that's a lot. And so these things are spinning around. Well, the little pieces of water in the air, it's like a tiny microscopic drill. It just goes right in between the fibers and explodes, right? I mean, in a hurricane, a typhoon, you see the blades actually hit the water so hard they fluoresce, and you get these green spirals, these green helices that fly off of these things. It's amazing. But that's also plasma. That's going to eat your blade. Good luck. I don't care what you put on there. It's going to get eaten. So, when we think about it that way, if we can actually take the robots that are capable of manufacturing these blade systems, and if they're small enough, if we can hoist them up the tower so we don't need to use people, and if the sensors and the automated programming of these robots is advanced enough, if we're using the same tool by which we had built the blade to repair the blade on the tower, that open chemistry, advanced robotics, they enable you to have a blade that's the same as it used to be. You can have a reinvigoration every year. Say, look, we know we're going to lose 5 millimeters of material every year. There's nothing you can do about it. It's plasma. You can't win. Fine. So then just have a plan to, like an oil change. But also, you could say, oh, the wind conditions have changed because, the seasons are different because, the world is changing. So we can go ahead and change the aerodynamic profile of the blade later on. That's never been done. So, and you wouldn't even have to demount the blade. This is why all this stuff coming together is, quite a technical achievement.
Yeah, well, and it also seems like, we were just chatting with the founder of Bladebug. We've talked with Nick Galdern from PowerCurve. They do lots of PowerCurve upgrades, vortex generators, gurney flaps, stuff like that. It seems like all those things could be easily just printed right onto the blade, where now they're a permanent fixture. They're not actually glued on. They're not epoxied on, but they're just essentially welded onto the blade. That seems to make a lot of sense. So why hasn't anyone, why has thermoplastic, I know you said it's still new, it's obviously 3D printing is still relatively new. I know it's been around for a while in its
about
current
40
form.
years.
We had Henrik Lund Nielsen, who's the founder of Cobot, on here, and they're doing a very similar work in just disrupting a lot of these industries, which they want to print wind turbine bases and potentially even foundations on site. So all this stuff, this is clearly going that way.
Yeah.
But I mean, what's the big holdup on thermoplastic, and why do you feel like everyone's so dug in?
I think one of the things is a valid critique, but it can be technically broken apart with a little bit more science, and that is 3D printing is slow. But where does that idea really come from? There's two places. One of them is I'm going to use one nozzle. So if I want to make a bigger thing in the same amount of time, I have to move that nozzle faster, or I have to make the nozzle bigger. So that's one problem. So parallel robots is a solution to that. There is no massively parallel 3D printer. There are some metal printers that use multiple lasers, but that's about the edge of it. Now, the other way to look at this is, a 3D printing is very slow chemically. So as an example, you can't stuff clay into a sponge. 3D printing continuous fiber and thermoplastics is not what I would call easy. And doing that injection of a highly viscous material into the fibers that are just going to get blown out of the way by clay, I mean, because that's really what melted plastic feels like, you have an issue there. So we've had to solve some chemistry challenges, fiber placement challenges, a lot of small things to really change the fundamental science. But, it's not easy.
Yeah. So before we get to, I want to talk about your Department of Energy grant and your partnership with the University of Maine. But I have a question for Alan. So, Alan, obviously in the aerospace world, which you guys all have a crazy combination of backgrounds, but you hear all the time that Boeing is throwing $300 million into a hydrogen project or into an electric project. It seems like a lot of these big companies in aerospace, and obviously the work SpaceX is doing in Blue Origin and NASA, there's so much theoretical stuff that they're just putting money into for the future. But it doesn't seem like that same thing is happening in the wind industry. Maybe it is in the background, right? They're very secretive. But Alan, why do you feel like there seems to be a difference in how much money aerospace and space travel will put into this sort of futuristic R&D and not so much on the wind side?
Well, I think it comes about because of the push to make aircraft essentially less expensive to operate, right? So in the aircraft world, we've been doing for 100 years, and so you have these systems in places and the knowledge and the engineers in place to try to minimize their overall costs. And so when you're designing an aircraft, you may choose a slightly more expensive product up front during the manufacturing side, knowing that the operational cost is going to go down. And those are the trade-offs that you make, because you know that an aircraft generally is going to last you 20, 30, maybe 40 years. In the wind turbine side, a lot of it early on was trying to get less expensive material, try to get something out in the field and get it up and running. And that shift is starting to happen now, I think, in the wind turbine industry, where the accountants and the people who are counting all the money to operate wind turbines are coming back to the OEMs and saying, hey, look, you're warranting our wind turbines for 5 years. After that, we're left on the hook with 15 years of maintenance and service. We don't want that anymore because the costs are so high. If we paid a little more for the wind turbine up front, we would save 15 years of, we would have 15 years or more money coming into our bank account. That's what we want. And the industry hasn't done that yet, but it will, because as soon as we get some of these bigger players in the ownership groups like the Berkshire Hathaways, right, the Warren Buffetts of the world playing in the wind turbine market, that changes. So the technology on the thermoplastics and moving away from thermal sets that we're already doing in aerospace and been doing for about 10 years or so, is going to also happen on the wind turbine market. It's just a little bit behind aerospace.
You guys have a Department of Energy grant, and you'll be collaborating with the University of Maine. And I know one of the big criteria from the Department of Energy in potentially, figuring out how to print wind turbine blades is that they want a 25% cost reduction. So can you talk a little bit more about this grant and your partnership with the University of Maine?
Yeah, certainly. Actually, it's Oak Ridge National Labs as well. So it's a three-way partnership between Oak Ridge National Labs, University of Maine, and Orbital Composites. About back in 2018, Cole and I sat down and we started talking about what are we going to do? How are we going to get into this industry? Because it's a heavily consolidated industry, very hard to get in, right? So we made a strategic plan. We need to develop some key partners. And we identified these two partners as our strategically the most critical partners that can really help us get this going. As you talked about, why isn't there more research in this area, right? There's many fundamental reasons, but we figured these two institutions are most well-positioned to do that. Why? Oak Ridge actually pioneered what's called BAM, Big Area Additive Manufacturing, and has been really pushing that into the industry, even so far as showing that you could use it to 3D print molds. So a natural partner, really excited about pushing this technology out. On the other hand, University of Maine is actually really special as well, because if you don't know, I would highly recommend getting Professor Habib on this podcast, because he is quite a visionary.
That guy's amazing.
And and I'll explain how, because he's been at it for actually a large number of years. But what he's doing is the University of Maine itself is actually making the first offshore wind farm in the US, the university. They have the largest 3D printer in the world currently. They have a large, I think up to 70-meter wind blade testing facility. They are one of the most foremost experts in what's known as biopolymers, materials, cellulose type materials that could be recycled over time. So, and they have what's called a wave pool, where you can actually simulate how an offshore turbine could work. So really a remarkable number of capabilities, literally in like two labs, which are right next to each other. It's just remarkable. So, and their vision of pushing printing into large scale, which nobody really kind of stood up and said, yes, let's do it. University of Maine said, you know what, let's do it. So we started working with both Oak Ridge and Professor Habib and his team at University of Maine, and really aligned on our vision that we all agree this is the right direction to go. And the current printers do not have continuous fiber printing capability. So that's one problem we need to solve. Second is the current printers are very rigid. We want to mobilize that. And so you have robots coming in. Robots has many advantages, the fidelity, but also the mobility aspect and the aspect of parallelizing printing. So what we're doing in this particular project with the DOE grant is DOE posed a challenge. You need to show 25% cost reduction. How do you achieve it? You can do it in different ways. You could start 3D printing the molds. That's one kind of low-hanging fruit, which has many advantages, both from a cost perspective potentially, but also from time to market. And as Ellen talked about the cash flow problem, right? You could actually print them much faster, easier, better use of cash. So that's one way. You also have another way where could we use additive manufacturing in a compelling way where you can cut weight out of your blade design. So the design aspect of additive, right? And the third is, how do you make additive competitive? Like as Cole talked about, you have to remember, we have to still compete with the current methods of blade manufacturing. There are two dominant costs in blade. Number one is materials. So you have to address that. You have to use lowest cost materials possible. And anywhere you can cut waste and save material, that's a benefit, right? So additive by nature is an additive process, meaning you will reduce material waste. It's not a subtractive process. So there's some opportunity there. But then I think, to be honest, the bigger opportunity is taking advantage of the ability of AM, additive manufacturing, and deposit material and fiber exactly where you want, rather than kind of spreading it all over the place, and optimize the designs and cut weight. So UMaine already has a large printer. They're going to make the molds for us. We're going to have this large, very disruptive printer system with very high speeds and very large scale capability, which will be developed by Orbital and then installed at Oak Ridge National Labs, which they have a very large facility where we will then demonstrate. We'll get the molds from University of Maine, we'll print the blades, we'll print a large number of them, but because we want to do many different trials and demonstrate various different types of capabilities with the new printing process, demonstrate speed, demonstrate ability to put material in different places, demonstrate recyclability, all in one shot.
And where does the mold come in? So if you're printing the blades, where does the mold come into that whole manufacturing process?
We are still using the traditional mold system, and we're depositing the material on top of the mold. And this is the best way to strike that balance between you need very high speeds, and these structures are also insanely heavy. So it's kind of, again, as we always say, right? You don't do additive just for the hell of it. A lot of practically, you end up, when you really think through a lot of these production systems, you have to think about the end product and their requirements. And many times it's these hybrid processes that are the most effective, where you
That's right.
exploit the benefits of additive, but take advantage of other benefits from traditional processes, right? So the
Mhm.
mold is necessary for that reason. We want to hit those very fast cycle times and be able to get cranking out blades like there's no tomorrow.
Well, that's good. That was really helpful because I feel like as I'm going through this, having not seen your process exactly like take shape, I'm just in my head imagining that this blade is sort of just growing out of the air. That's not really the way it's going to happen. You're going to use the molds and you're going to use a combination of current technologies to find the most sensible solution. I know Al and I have talked a bunch about that. How we've been talking about the EVTOL sector a lot in our other podcast, and just how the most successful companies are probably going to be the ones that you reuse a lot of just proven technology combined with some new technology rather than just try to reinvent everything under the sun all at once, which is really, really hard. So that makes more sense to me conceptually. I'm sure it does a lot for our listeners as well.
We're able to very precisely control where each fiber is going. And even in the actual aerospace industry, they rarely do that, especially in commercial aerospace. They're going, no, it's 90 and 45 and 135 and 180, and that's all you get.
And you're talking about the carbon
The
fiber
fiber
weave.
placement. Yeah.
Mm-hmm.
Well, even if it's tape placement, it's still 45 degrees or nothing. There's not a lot of curvature going on. Tapes don't do that. But even if you look at traditional wind turbine blades, they're basically like people rolling out big woven mats. Well, if you think about it, you're weaving a sheet together. Now, even if we forget trimming the edge of that sheet because it's going to be a rectangle, but even thinking about the fact that half the fibers are going the direction you don't want.
Right.
And so we're saying you're going to take those fibers, you're going to put them exactly where they need to go. So when you think about it, an aircraft might have what we would call 20% embodied waste, which means because the fibers are pre-woven, or because you're limited by the number of angles you're going to pick, you're building fiber orientation that's non-optimal. The optimal
Right.
thing, you already know what it looks like. It's a leaf. Those fibers need to be
Right.
branching and they need to be spreading out just like this as they go up the blade. That's
Right.
natural. We're not even close to that. So this single fiber placement at rapid speed, every fiber has its own history, all that history is recorded, and if there's a mistake, the printer will fix that problem automatically. That's really
Right.
what you need to be able to have something that enables you to have potentially unique blades made in the field, one off for this tower, born certified. It's a very big challenge to do that with individual fiber placement, but you look at the savings of the embodied waste, you could potentially also then look at the savings of a lower cut-in speed or better optimization for this wind regime.
So correct me if I'm wrong. It sounds like you could probably reduce weight of the blade if you
A
don't need
lot.
as much material because the fibers are so much more effective going, like you said, the directions that they
In the right
ideally
direction.
would go under perfect conditions.
Yeah, and changing those fibers. You have high performance carbons over here, low performance glasses over there where it makes sense. Because some parts of a wind turbine blade, you just need something that acts like concrete. And at the tip of the blade, you need something that's a helicopter blade. There's a
Hmm.
big difference in those physics. So you need to have your materials be produced in that fashion. It's not just fiberglass.
No, that
So
makes a lot of sense. And you could change it over time.
cool. And so is the thought process then in terms of the sort of robotics of fiber placement in a 3D fashion, dry fiber and then applying the thermoplastic or thermoset, I guess you could, to the fiber as it's extruded. It's like it's all one in the nozzle situation. So you're actually buying cheaper non-prepreg fiber and then your own separate resin system, whatever that is, and you're right before it's applied to the product, you're putting those two together and laying the bundle down, not a tape down, but a bundle.
Yeah, right at the last second. Because you think about the machines that actually make prepreg, they make tapes, they could be 4 stories tall and 400 feet long. They run at 100 miles an hour. That's not cheap.
Right.
And then you have another step in the process. You think about weaving, then that's another step in the process. Well, how about you just take the spools from the spool factory and you stuff those into a printer?
Right.
in the field. You're taking
Right.
steps and steps and steps and steps out of it. That's the key.
Right, exactly. Freezers, expired material, all the lost waste and costs that are associated with all the transport issues go away. If you're taking dry fiber and taking a resin or thermoplastic material, which are the cheapest forms of both of those things, and then
Exactly.
bang them into a composite material at the last second, yes, I think you've then honed in on the true lowest cost option, and obviously the versatility of how to place those fibers explodes the engineering possibilities in terms of what you can design and what you will design, because you finally can control it and know that it went down. And one of the issues with hand placement of fabrics versus the automated tape system was when we switched from hand-laid placement of fiber of cloth, was we weren't always sure that we put the right amount of cloth down, so we always put more in, right? So we added weight because of the human factor. We went to tape placement, we could eliminate some of that. When you're going to this level now, you'll know where every fiber is and what the resin content is when it goes down, and you have a record of it. For every part that's manufactured has basically a quality statement that comes with it. Like, we know exactly what's going on with that product because we recorded it as we did it. That's amazing. That is truly amazing, and that's groundbreaking. And that's why I'm so excited as you get into doing this effort, that the output of this is going to be tremendous. It's just going to be tremendous.
Yeah. Thanks, Alan. And we've worked long and hard to be able to produce a robotic system that meets all the requirements for Industry 4.0, which you just linked together very well. And also, if you think about it, a lot of these blade systems are made by hand also on the resin side. It's not all vacuum infusion. There's adhesives,
Right.
there's other things. So you're looking at blades that could be, plus minus 100 kilos or more. So, if we have the ability to titrate our chemistry very precisely using robotics, using our machine learning and so on, then you're looking at the ability to have blades that, when they're produced under the tower for that tower the first time, are matched within a kilogram or so. Right. As opposed to, I've produced 50, 100 blades of this model, and then I just pick the ones that are less than 50 kilograms off from one another, and that's a matched set.
Right.
Well, what if you have the ugly duck? Garbage.
Yeah, it sits in the parking lot. That's what happens. Yeah.
The point, Alan, you made earlier about, again, all these blades sitting around, you can't ship them until you find a matched pair, right?
Right.
So these problems just perpetuate, right? You've got, so there's so much room for improvement here. And there's one thing I want to add. There was a question around the business model and why people are not making this change to thermoplastics, right? I think there's some structural, challenges in the industry, because the blade guys, their business model is selling blades, and as many as they can. And it turns out they're making plenty of money fixing them, becoming a big part of their business and very profitable. So I think the motivations of the industries are not well aligned. Whereas if you look at it from the operator side, of course they want long life, right? They don't want to repower the wind farm they just made 5 years later, right? So there's some fundamental tension here in the industry. And I feel like there is also opportunities to rethink the whole business model. And really, I think a new crop of blade companies should really think about this in fundamentally different ways of how do you truly become partners with the operators and be incentivized in a way in the business model where you are motivated to make blades that actually last. And maybe there's a servicing model which is different. You have there's options here, but I'm just pointing out the way the industry is set up is part of the problem.
Yeah, and that's a similar thing with electronics, right? I mean, there's battles for right to repair in electronics. Companies are fighting with Apple. The reason I'm recording on a Windows laptop is because it saved me $1,500 because I could put in my own hard drive, my own, I could add more RAM to it. Whereas if I buy an Apple computer, guess what? It's going to be soldered in there. I can never upgrade it, and I've got to choose right when I buy it what I want the specs to be, and that's frustrating. It doesn't let you grow with it. And the right to repair thing that's gonna be, I think, a big congressional fight coming up soon, because there's a lot of people who say, look, I own this product, I want to be able to fix it, I want to be able to upgrade it if I have the tools to do so, and companies shouldn't be allowed to, prevent me from doing so. And that's of course not what we're talking about here exactly, but we're talking about the built-in obsolescence to a degree. Like you said, blade companies want to sell another blade in 5 years if they can, not 20 years from now. If you make something too robust, you don't get to sell anymore. Let's transition. I want to talk about recycling, which is obviously another big benefit of thermoplastic. And like you mentioned earlier, you alluded to the Bloomberg article where there's decommissioned blades in Illinois. We saw that and we talked about it on an episode back in the summer. You see these graveyards of wind turbine blades, and they can't really go anywhere. It's really hard to chew them up because, what grinder can even take one of those into it? It just seems like such a difficult problem. How would 3D printing and thermoplastic change the scope of recyclability?
Back in the 90s here in Silicon Valley, there was a wave of investment that ultimately became a popped bubble. And that bubble was called green tech. So back then there were a gamut of companies that sprang up, and they were going to save the world. They were going to give us cleaner water, cleaner air, and cut pollution, recycle things. But basically, all of those technologies that were being offered at the time didn't meet scale economics, or they couldn't meet the dollars per pound or the dollars per kilowatt hour. They were fundamentally worse than everything that came before them in the traditional manufacturing or energetic economies. And so when you think about doing a startup today, one of the things is that you need to go for, as Peter Thiel would say, a step function. You need to go from 0 to 1. You need to be 10 times better than everything else. You can't just go into Main Street and put up another, $20 a plate restaurant and just beat them on looks alone. You're going to get tired. You can't win that way. So when we think about what can we do, why do we need recycling? Why do we need mobility? It enables you to get to places you could never go before. That's your step function. The blades get longer. They couldn't be that long. The rotor blades get new shapes that you couldn't have before. And ultimately, you stop buying material as your company continues to grow, or you buy much, much less material because it's a concave down function. So all those things can combine to give you a company that's, 10 times more efficient. And when you look at the operating margins on a lot of the wind turbine companies, they're very tight. It's unfortunate. But I think that's one of the other things that limits their technological progress and their appetite for risk. They don't have, $150, $300 billion of government money to go try making some new aircraft that may or may not make it, but we're going to learn something. If they have towers blowing up, they get in big trouble. So, that's why we're here to take that risk and to really then push the green technologies using these digital transformations.
I basically like to hear you guys sum up sort of like what you feel like your end product package is. So say like I'm a wind site operator in the future, and I say, hey, this sounds great. Sign me up. Our wind site, we want to use, your manufacturing. What does that then look like? You guys truck your container with your microfactory in it, but it's kind of like take me start to finish what you feel like that looks like when you guys get to that point.
Yeah, I mean, this would be a great time to take a look at the video that we'll go ahead and attach. And so, in the video, here's what we're looking at. We've got a wind turbine field, our location of interest. We're going to truck in shipping containers. By the way, shipping containers, 40-foot shipping container, that's about $1 a mile. It's a very, very low cost. Whereas look at those specialized trucks to move 55 or 60-meter wind turbine blades. Not $1 a mile. And they don't go through the international network. They don't go overseas, right? And so we have then at the base of these towers a factory that's basically a series of like a bunch of jack-in-the-boxes. Right? So you have the shipping containers, they're stacked. The robots jump out of the boxes. They all meet in the middle, and then that's where they can print the mold. assemble the mold, and then go ahead and do the fiber placement operations and finish the blade. So that sort of mobile system is really the long-term vision. And then the cool part is, it works for different blades of different sizes. There's plenty of blades out there that are out of date, obsolete, old wind turbine fields, loaner turbines where the manufacturer is no longer in operation. So those are the places where we can help in the early game. And then when you look at the late game, our vision is to have a full-size shipping container vessel. We can move our factory anywhere in the world. It's just a bunch of trucks after all, and then produce the blade that you need right under that tower.
I think that all makes sense, right? So South Korea is in a big push right now to create offshore wind turbines, and they have a large manufacturing base to make ships. Those two go together. Clearly, there's going to be an effort to start making wind turbine components on ships near the site where they're going to be placed. All that makes sense. And I think finally we're going to get to the economics of the full lifetime economics of where and when you're making your money. You like to recover your early investment as early as you can, but the remaining part of that time, you just like to be making cash flow, right? Yet your repairs are minimal, but your influx of cash is high. There's your ideal spot to be. And until we sort of rethink the whole life cycle, including all the bonds we put up to decommission wind turbines and the cost of that and the cost to recycle all this stuff, then we're not really getting a true measure of how much it costs to operate a wind turbine. This is going to change because of the opportunities like Orbital Composites is going to bring, which can change that economic model. And once you start changing the economic model, the accountants will start to pay attention and the investors will start to pay attention and force it. It will no longer be an engineering decision, like in a lot of cases. It'll end up being an accounting investor decision of where they're going because they're putting up the cash, not the engineers. And that's when large-scale changes will happen. That's when it's going to occur. So it's coming. It's just on the precipice of it. Next couple of years can be really important about when that transition happens.
Well, guys, we really appreciate you coming on the show today. Where can our listeners follow up with you both and with Orbital?
Yeah, we definitely would recommend your viewers check out orbitalcomposites.com. There are many links on there to the different podcasts or webinars and things. We actually do give a lot of talks to the composites industry and beyond. Definitely worth checking out, I think. It's not all about our stuff. We talk more generally about the future of carbon fiber and energy technologies, other things. And then sign up for our newsletter. Tap that subscribe button. And, take a look because we've got a lot of interesting things coming at you. It's fun.
And my contact is same, just first name, both for me and Cole, first name at orbitalcomposites.com.
All right. So for all of you listening, definitely check out the links in the description below, whether you're on YouTube or in podcast land, and you'll be able to click right through to Orbital Composites website. And we'll also link to wherever you can find them both on LinkedIn as well. So thank you again, guys, for coming on. This is a really great conversation. We appreciate you.
Yeah, thank you very much.
Thank you for having us.
Let's give a quiz to the readers. How many miniature wind turbines were in this podcast?
All right. Well, that's going to do it for the Uptime podcast today. Be sure again to check out the links in the description below where you can learn more about Orbital Composites. And again, thank you to our guests, Amol Ekbadesha and Cole Nielsen. Again, we appreciate you listening or watching here. We're on all podcast platforms and YouTube. So be sure to subscribe to the show, share it with a friend, and we will see you here next week on the Uptime podcast. Is downtime causing you financial pain and putting a stop to your power production for months on end? It's no secret, lightning strike damage is a major cause of wind turbine downtime. This damage is preventable with our easy-to-install Strike Tape lightning protection system for wind turbine blades. Our incredible engineering, build quality, materials, and edge sealants withstand up to 5 times more abuse in the toughest weather and lightning conditions. And we've got the research to prove it. If you're tired of constant downtime, we can help. Reach out to us at weatherguardwind.com and schedule a free call. We'll get your uptime back in no time.